And today we'll be talking about Combustion Analysis 101, and we'll be talking a little bit about some of the UEi Combustion Analyzers, especially the C161, which is a brand new one. So I want to do a quick poll here to find out who is in the audience, who's listening today. So I've got the poll launched right now. You could just click on what your field of work is. That's good. Okay. Got almost 70% of the people voted. All right, we'll go ahead and close the poll right now. Just want to get a little snapshot of picture, and I'll share the results. So you should be able to see the results here that 64% are in HVAC, 18% in building or home performance, and 2% are in, or excuse me, 18% are in other. So thank you for doing that. That helps us sort of figure out who's listening to these sessions. So my background, just to give you a little bit of background, I've been trained in engineering, worked for Bacharach and Testo for 10 years each, and been with Trutech now for 10 years, going on 11, coming up in February, just about a month from now. I also do a couple of podcasts, Building HVAC Science and Res Talk. That's for ResNet, the home energy rating system. A lot more people are listening to podcasts lately, and we're using it as another way of communicating. And I do a lot of guest interviews on both of those shows. So it kind of gives you some insight into the people that sort of we talk with, the Trutech people that I talk with. My email address is right up there, and you should be able to see bill@trutechtools.com to be able to reach out and get in touch with me. We have a question and answer panel, or a question panel that I'll see pop up. I have running here in another display. So if you want to shoot over a question about something you're seeing on the screen, please go ahead. A little background on Trutech. We're founded in 2007. We have now 15 employees, those smiling faces you see in those black shirts in the lower right corner of the page. Over 80 brands of products. We carry about $1 million in inventory, and we did 2019 was about 13.6 million in sales. So we've grown very nicely. We want to thank you, our customers, who's helped us get there, and we want to continue to serve and grow. We've been awarded a couple times, 3 times actually, with the Inc. 5000 award for fastest growing U.S. business for those 3 years shown there, 16, 18, and 19. We do participate with RSES, ResNet, BPI, ACA, and other organizations to stay tuned into the industry, and we communicate these things through telephone, through our website, through trade shows, through webinars, through podcasts. So we try to stay engaged and be good stewards of the industry. So I want to quickly run poll number 2. And okay. And looks like, sorry, now I got it. Excuse the guy behind the green curtain. What's your familiarity with combustion testing? No familiarity. You've done a few. I test problem units, or I test on everything I work on. Okay, this is an interesting mix. It's kind of rising there to be about the same percentage in those 4 categories. Okay, got 82% of the people voting. So I'm going to close the poll. Gives us a nice sampling of the results. 20% no familiarity, 33 done a few tests, 20% test the problem units, and 27% testing every unit they work on. Thank you for sharing that information with us. So why is it important to do safety and performance testing? That's really what we boils down to when it comes to combustion analysis. It's usually for safety and performance. And performance can be sort of comfort performance as well as fuel efficiency, durability, that kind of thing. So we see a listing of different things. I want to kind of go over those things with you. This helps you ensure appliance safety. Of course, safe operation is really critical for your customers. Minimizes your liability. Of course, if you employ safe practices and you have a safe setup, it should be able to keep your liability down for being responsible for ill-performing equipment. It improves preventive maintenance and fuel savings, and this is especially true for commercial accounts. And then just for any part, the better you are at your skill, at your trade, it improves your company's professional image. And even in some cases, anecdotally, we've heard where equipment manufacturers are very impressed when they see a customer or a contractor that actually does do combustion analysis. It helps them out. So we got one question here. All right, that was actually just a request for questions. Okay. It also helps increase your company's profits because you can do more exacting analysis, quicker service calls, minimize the callbacks, and in fact, create a revenue stream by adding combustion analysis to one of the things you offer to your customers or clients, which helps satisfy their interest in their comfort, security, energy efficiency. And there are also national installation verification programs. ACA actually has one. It's called the Quality Installation and Quality Installation Verification Program. Look up those two words there with ACA, and you'll find a standard that's actually been written. And I helped on the QIV standard, help write sort of the correct processes, really start to put it into one place, into one code of how to do correct and proper processes. So now, why would you test an unadjustable appliance, something that typically people think of as not being adjustable? Well, a lot of this has to do with the equipment being installed in a dynamic environment. And this is especially true for, we'll call it mid-efficiency to low-efficiency systems, which can be affected. The combustion air can be affected by pressures in the combustion air zone, the zone in which you're pulling the air from for combustion. Any system can be affected by fuel pressure or fuel quality. It's the rate of delivery of the fuel, of the hydrocarbon to the system. It can be affected by changes in blower speed. Part of the system is designed to work at a certain rate of energy transfer, of heat transfer. If the blower, and we're talking about warm air distribution combustion, if the blower is moving at the wrong speed, too much heat can build up or too much heat can be taken away, which can change and affect the performance of the system. It can even get down to duct or air sealing. One way in terms of like a leaky return can actually pull on the combustion air zone, or in a leaky supply situation that could waste heat that goes into the wrong location in the structure. And affected by things in the environment it's installed in, chemicals, anything that happens to be in the air that's not supposed to be in the air that can get in and be changed chemically in the combustion system. And also by the installation itself, the pressure, the total external static pressure, which can change the way the air flows. And that gets back to sort of the same idea as the concept of the blower speed changing. And maintenance, filters, again, affecting the airflow. We're talking warm air heat exchangers and heat being taken away at the correct rate, the designed rate. And also by remodels of the space, of the ductwork, of even the equipment, or homeowners attempting to do repairs on equipment. All these things can change. And that's why it's a good idea to test all the systems like some of the people are, and they're shown in the poll. So we're on poll number 3 here. This will be our last poll. Going to launch it. So do you have access to a combustion analyzer? Do you actually have one that you can use? No, yes, and it's shared. Perhaps one it's shared by the service manager or somebody in the shop, and you just call on it when you need it, or you have one of your own that's issued to you, or one that belongs to you. Okay, we got over 70% of the people voting here, and I'm going to close the poll and share it. So it looks like most people here own one or has one issued to them, and that's great. So that means you are able to do that testing more frequently. You don't have to wait around for the next one to be available. Okay, that concludes our polls. Thanks. So this is an illustration of complete combustion. Starting from the bottom part of the screen, you see there are 3 main elements. Sometimes you hear this described as a combustion triangle. You need oxygen, fuel, a hydrocarbon, H and C there. So remember that this is a little bit of chemistry we'll be talking about, and a source of heat or ignition. And these, in the correct proportions, will combine to perform complete combustion, which will release larger amounts of heat than the heat that went into it. And that's due to the chemical changes between the oxygen and the fuel, changing the carbon in the fuel to carbon dioxide, picking up some oxygen, and the hydrogen in the fuel to water vapor. So H2O, you can see the hydrogens here, and O is, of course, the oxygen, and CO2 coming from the carbon and the hydrogen. So this is if everything runs completely correctly. You can also consider this as undiluted combustion. There's no extra air present. So this is if you've got everything tuned right down to the point where only oxygen and fuel are going in. But I think as most people realize, you're using air in combustion, and air is made of nitrogen and oxygen. We'll be talking about that. So you can never really reach this unless you're in some special process or lab situation. So like we hinted at there, air is mostly nitrogen, 78% nitrogen, about 20.9% oxygen, and about 1% other gases. And because of that, you need a lot of air to get the right amount of oxygen. So if you need 2 cubic feet, for example, of oxygen for combustion, you'll need to pull in 10 cubic feet of air because air is only 1/5, approximately 1/5 oxygen. So this gives you an idea. There's other things going on or moving through the combustion system beyond just oxygen. So because air is the primary source for the oxygen in combustion, you can never get to perfect combustion because you always have that extra nitrogen flowing through. So large amounts of heat energy are also absorbed by the nitrogen, and they're entrained or carried through, and they play no role in the combustion process, but they're carried through as part of the exhaust into the flue gas exhaust. So going back to this illustration where we left it a minute ago with undiluted combustion, perfect combustion, let's look at what we call more complete combustion. Look at more of the elements that are actually happening here, get a little bit more refined, or even incomplete combustion when things don't go correctly. So air, now we've expanded the definition of air in our little simple diagram to have about 1/5 of it be oxygen, most of it be air, and stuff or other things that could be entrained in the air. These are things like hydrocarbon vapors, cleaning solutions, things like that that could also be in the air. As you move through, now you still get the CO2, the water vapor, and heat, but if you don't burn to completion, you'll also get CO. That means that the carbon could not find and merge with 2 oxygens. It only found 1, so it produces carbon monoxide, and mono means 1. So you have a situation here where in incomplete combustion, you can develop carbon monoxide. And we'll talk about what causes incomplete combustion in a couple minutes. You can also have excess air, just that extra air moving through the system. And sometimes there's even excess oxygen and just the nitrogen part of the air moving through the system. Various toxics can be present, and those toxics can actually be formed by stuff that's in the air or the fuel. If there's sulfur in the fuel, for example, if this is, say, oil system using a higher sulfur oil fuel with hydrogen sulfide, you can get sulfur dioxide gas. The nitrogen in the air can also form with the oxygen, and in many cases, you'll see nitric oxide, NO or NO2. It's not something we typically test for unless you're doing some emissions type work. And you can also get soot, and the soot traces back. It's got the same color as the fuel because soot is basically carbon particles that have formed together. So it's just raw carbon. So this is sort of gets into the more complex analysis of what can happen in a combustion situation. And what I've done here now is added, this is your stack. It's laying horizontally, but this is your stack. And this is what the combustion analyzer probe actually measures. So what it does is you can make inferences from how combustion is operating from what you measure on the output side. So that's what your combustion analyzer does, is measures the temperature and the constituents, the elements that are in the air, and does some calculations to tell you what's going on. These two parameters together are CO air-free, carbon and the excess air. So we'll talk about how that's developed inside the analyzer, how it's calculated, and what it actually means. But keep in mind, those are two things that you can measure. Is CO air-free, it's a combination of knowing how much oxygen or excess CO2 is in the air and how much CO. So we talked a lot about air. Why do we care so much about it? So the illustration on the right is a lower efficiency furnace, which is requiring several types of air. It has, of course, distribution air that's moving around the heat exchanger chamber. That would be this kind of white arrow that's moving through here. The combustion air, which is moving in, merges with the fuel and moves up through the heat exchanger, and dilution air, and then taking it out the vent system. So you need to know what the sources are for your air and what they're being used for, and you don't want to upset the balance. So for example, Ventilation air, I consider as air that's coming in purposefully with a mechanical system that's bringing in fresh air into the structure. Infiltration is air that comes in through the leakage pathways. It infiltrates. It's not meant to be there, but it just happens. Makeup air sometimes is provided for combustion systems, other times it isn't. So if you look back at, and of course they're being used for combustion dilution and then just the distribution air or breathing. If you look back at this and say, well, I want to get control over my building structure, how leaky it is, it's drafty, let's really address the infiltration. So when you do address the infiltration, that might actually be a source of air for combustion or for dilution. And I've actually worked on some expert witness cases where that's been done, where they really sealed up. This was a manufactured house. They really sealed it up tight, and they caused a furnace that wasn't operating poorly before to actually poison someone because it was using infiltration air in its combustion process. So you have to be very much aware of the air. Combustion efficiency equations are part of every combustion analyzer. And there's actually now a performance standard that's written by the AHRI, the Air Conditioning, Heating, Refrigeration Institute, which is a member organization of all the manufacturers that are involved in air conditioning, heating, refrigeration. I helped to start this committee a number of years ago, and the standard actually came out in 2017. And the standard for the efficiency equation considers stack losses and combustion efficiency. So part of it's due to the thermal performance, and part of it's due to actually how you create that temperature. And the high efficiency equations are also baked into the standard, to the new standard. And these are always automatically done in the analyzer. It used to be that you had to look them up and use a slide rule calculator, and that dates back probably 30 years. But now they're all done. You get the combustion efficiency. And this new standard, you can check to see if your analyzer is compliant with the standard. It should be listed in their specifications, or if it's one that we carry, we try to list that on our website. So you can pick up the standard for free at this short link here, bit.ly/AHRI-1260. It'll take you to a PDF of the standard. Some interesting reading if you're into the geeky parts of combustion analysis. It'll tell you how the manufacturers are trying to design equipment that can provide consistent readings, and that's what we all want to have. So let's take a minute and take a look at the combustion diagram. So the left axis is showing the increasing amount of the flue gas components, the increasing concentration or levels. And then the lower axis, well, we'll talk about the stoichiometric line, which is the point of perfect chemical balance, where you have just the right amount of oxygen. Remember that very first slide we show with the little bubbles on it had perfect or complete combustion. So on the left-hand side, you have incomplete combustion. On the right-hand side, you have complete combustion, and it just starts to become complete at the stoichiometric or the chemical balance line. You can also think of the left-hand side of having too much fuel and the right-hand side of having excess air. So this would be the amount of air going on the bottom axis, increasing concentrations of air going into the combustion system. Usually do this by measuring oxygen, although there are analyzers. We'll be talking about one, the EOS sensor and the C161 by UEi that actually does measure CO2 and calculates oxygen. Same thing, you can go both ways of the calculation. So increasing air going into the combustion, you'd see the oxygen number start to appear and start to rise. The CO2 level there's more air going into combustion, it would start to reach a peak and then drop off due to dilution, whereas the oxygen concentration would increase due to excess air. The carbon monoxide line, generally speaking, decreases, and you're at the point of where you're decreasing the amount of carbon monoxide created. Then after this point, when it reaches the stoichiometric line, you have excess air, it actually starts to dilute the concentration. And then the efficiency peaks about the same point that the CO2 level peaks. You can also see if it's a oil burning or even propane, and sometimes natural gas, you can see smoke coming from these systems. The smoke amount, which is the raw carbon, does tend to decrease as you go towards higher amounts of oxygen, higher amounts of air in the system. And the good operating band would be this green bar in the center here, which is an operating with some excess air. You want to make sure that, because flue gas does change composition even across the stack, even across the exhaust tube that you're measuring it in. So you want to use flue gas sampling by looking for the hottest spot to find the correct place to make your measurement. So that's something you can do with the analyzers, is watching the temperature when it reaches the peak. That's when you want to snapshot the combustion gas measurements. So we did mention we'd be talking about CO air-free, and that would be undiluted CO. So you can actually mathematically undilute it by taking a ratio between CO and the amount of oxygen or the amount of CO2. Again, the calculation goes the same way. This corrects for excess air. This requires a combustion analyzer with either an oxygen or a CO2 sensor. And usually it's used in appliance measurement, but more and more it's becoming used in stack measurements. If you're familiar with BPI, the Building Performance Institute, actually their standard BPI 1200, released in 2017, has a table of CO air-free measurements for various types of equipment that comes from the ANSI standard. We'll show that in just a second. And here you go. So this comes from the BPI 1200 standard. If you want to go to that link at the top, type it in exactly as you see it, bit.ly/BPI-1200-2017. You'll find table 1 in section 7.95 that tells you what the limit is. Generally speaking, 400 ppm when measured on an air-free basis. However, ovens and broilers are as measured. That means the raw CO. Refrigerators, there are actually combustion refrigerators. Some of you might be familiar with that. They get as measured gas logs as measured in the vent, and the gas logs installed in the fireplace, 400 ppm air-free in the firebox. So these have been developed by consensus with the manufacturers and other practitioners and those interested in the field. So sometimes this concept of CO air-free is a little bit hard to understand. So my friend Rick Karg from Maine had this analogy. I had another analogy, but I like Rick's better, so I stole it. The concept of undiluting. So let's take 3 glasses, one with no water in it, one half full of water, and one full of water. Now let's add 1 dropper of food coloring, the same amount, 1 dropper of food coloring. And the food coloring is going to be considered to be the CO, the thing that we're interested in measuring. And as you can see, adding it to each of these glasses, you're going to get a different color. That's the concentration of your color or concentration of your CO. So which one has the higher concentration? Of course, it'd be the one that's the darkest color. It has the highest concentration of CO. It's got nothing diluting it. If we could evaporate the water, which means removing the excess air, we'd have the same amount in each. So the process of undiluting or providing an undiluted sample allows you to get a consistent level of the actual CO being produced in the system before it's being diluted. That's the purpose of doing this, so that measurement to measurement can be done consistently. Just throw up another illustration here going back to the stoichiometric line, but we'll look at it more simply with oxygen and CO level. As the oxygen level increases, the CO level decreases, not because less CO is being made, but because CO is being diluted by increasing concentrations of air, which the oxygen is telling us about what's happening with the air. If we could remove that factor of oxygen, the CO air-free would look like the same number, like taking it back to the stoichiometric line for the whole range of testing for excess air. So I'll do that one more time. Here you see a declining amount of CO. Here you see a consistent amount of CO air-free because of the calculation of CO air-free. Another important factor when making measurements is how your analyzer works. What are the sensors doing inside? We talked about nitrogen in the air combining with oxygen, making different oxides of nitrogen, nitric oxide, nitrogen dioxide, dinitrogen pentoxide. So we also have nitrogen, which is created in the air. It can be present in the air, in the flame, or in the fuel. And that can convert or create nitric oxide or nitrogen dioxide that comes through the stack or the system. The whole point of this is nitric oxide, the NO component, tricks a CO sensor. It's also an acid gas. It makes the CO sensor think it's sensing CO. So for example, if you had 100 ppm nitric oxide, it would show up as 40 to 50 ppm false CO. The way around this is adding a NOx sensor, or excuse me, a NOx filter. You don't need to measure it, but you just don't want to measure it and think it's CO. We get a lot of questions with that. There are still some analyzers on the market that do not have nitric oxide filters, so they're going to report higher values. Then when you compare them to one that has the filter in it, and you think, well, the one with the higher value's got to be right because it's sensing everything. The other one is wrong. Well, actually, it's the one with the nitric oxide filter that's correctly sensing only CO. There's also a fact that hydrogen fools the CO sensor. It can make it think that there's CO present when there's hydrogen present, but you only get that hydrogen if you think back to the hydrocarbon fuel. Only when you have very, very low amounts of excess air will you find hydrogen being produced typically in a combustion system. So this isn't something usually encountered in residential or commercial, who's usually our audience. If you want to get more info on this, we actually did a paper when I was with Testo, bit.ly/NOx-truth, all uppercase. It'll take you to a PDF where you can learn a little bit more about this. So if you want an accurate flue gas reading of CO, you should never measure without a NOx filter. This may be an internal filter on the sensor. And in fact, this one is the NOx compensated CO sensor in the UEi C161 that I took apart a couple weeks ago. You can see right on the label, onboard nitric oxide filter. Or it could be an external cartridge that's built into the that's added on to the sampling hose. And we actually sell a brand called Correct Measurements, NOx filters. If you're not sure, go back to where you bought the product or come to us at Trutech and we'll help you out to figure out whether or not you need a NOx filter and what state it's in. So I want to get into some of the new features of the UEi 161 and show you how they're actually benefiting the way you can use the product. It's got replaceable rechargeables, nickel metal hydride, and a USB charger. It also uses standard thermocouples for those of you that are interested. Someone just asked the question, does Bacharach have one? Yes, some of the Bacharach analyzers do. The Intech line does not. The Insight line does. The PCA line does from Bacharach. And I believe at this point, all the UEIs have the NOx filter. So good question, John. Thank you. It also has a nice lightweight probe with dimples in it. The dimples keep the darn flue gas sampling cone from dropping off. It's a nice little creative idea. I'm not sure exactly the process, how they did that, but it keeps it from sliding off the tip of the probe or sliding back too far in the other direction. So that's a really nice feature that they have. So one of the other features you talked about was I alluded to before, some combustion analyzers sense O2 or oxygen, and some sense CO2. So now we're going to talk about the difference because you will find this in several models of the UEi combustion analyzers that's really different and unique amongst all brands that are on the market. So on the left-hand side here, you can see we measure CO and O2 in your combustion analyzer, and the electrical signals from those will come in and they'll be reported on the screen. And from the oxygen level in the fuel code that's given to the device, it will calculate the CO2 level. You got to remember, oxygen sensors are always on. They're pretty much always active since birth. They react with the air around them, and they continue to deplete. As their voltage drops below a certain point, that's when you get your sensor failure or sensor end of life signal from the analyzer. For the UEi combustion analyzers, they use a different technology. They use a non-dispersive infrared sensor. So basically you have, of course, the same CO sensor, which we talked about. NOx filtering is really important. And then they take the sample gas and pass it through a filter. The filtered light will absorb, it'll be emitted from one end and absorbed through a filter in the other, and in the spectrum where it absorbs the CO2. So this is like a very sophisticated type of lab bench measurement. In fact, the organizations that measure really high-end equipment use non-dispersive infrared analyzers. And this is a miniaturized version that you have in your hand when you have these UEi analyzers. So it measures the absorption of infrared energy in the range of the CO2 sensor, and that censored here detects the difference in light, which will then give you a CO2 level. And then the CO2 level with its flue gas, the fuel code, creates the calculated O2, calculated oxygen. An interesting thing here, as I point out on the display of the screen in the 161 as it's starting up, it has ATM. That's not the place where you get the cash from. This is the atmospheric pressure of 983 millibars. This is very important because it senses the atmospheric pressure, the barometric pressure, because that affects how a non-dispersive infrared sensor works. So this is actually an internal correction. You don't need to know about it except it's there and it works. But it's been built in by UEi very thoughtfully to give you a very good CO2 level when you're doing analysis. Without that, you'd have a little bit of difficulty as you changed altitude. The CO2 level would get a little bit fuzzy, but with the built-in correction factor with the barometric pressure sensor, you get a nice stable CO2 level. And they call it the electro-optical sensor because it uses electronics and optics in order to detect the gas. NDIR stands for non-dispersive infrared. That's the way the sensor technology works. Okay, so we've rolled through here in just a little bit over 30 minutes about some basic combustion and how some of the features of the UEi combustion analyzers work. John asked, will this be available on YouTube? Absolutely. Give us about 2 days and we'll post it on the Trutech Tools YouTube channel. If you just go to YouTube, type in Trutech Tools, it'll take you to our page. We both have a category for combustion and just also like our latest video, so you can find it there within a couple days. We did another session just like this last month. The audio recording wasn't as good, so this one we're talking on today will replace the one that was in December. Same basic content, just better audio. Okay, any other questions out there? Be happy to answer. Okay, so thank you for attending this session. Best thing to do to keep up with other sessions that we offer, if you go to trutechtools.com/events, you'll go to our events page, and on that page we have our webinars, the trade shows that we're at. We should actually post our podcast there too. We don't do that at this point, but that's a good idea. We should post our podcast there. So it's sort of like our external media connection that's off our website. We'll make sure our blog is linked there and that kind of thing too, just so you can get to kind of sample all the different things we do. You know, doing this now for almost 13 years, we've got a lot of media, a lot of knowledge that we'd like to share with our customers out there. We really appreciate you for listening in today. And here's just a little closing. Thank you very much for attending and listening. You're welcome, Jeff. And if you haven't listened to podcasts, try it. You'll like it. A lot of people do. A lot of technicians usually have windshield time. And that's probably a great place to get a little extra thoughts injected into your head. Zach is asking, is there a big difference between the Testo 300 and you didn't finish your question? Between the Testo 300, perhaps the UEi analyzers and the UEi. Okay. The Testo 300 is, I would say, sort of an upper middle range analyzer. It's actually got, I think, 8 different models, and I would say like two or three major breakpoints in the configuration with NOx sensors and things like that, color displays. The UEi 161 that we showed here is, I would call it it's a great entry level model, in similar kind of framework to the Testo 310. And then there's upper level UEIs like the 165 that gets into the range of like the Testo 300. So we can also talk about these things specifically too. If you want to drop us a message to info@trutechtools.com, give us a call, 888-224-3437, or chat with us live on our website, or leave a chat ticket if no one's available live. Okay, I want to thank you all again for listening, and we'll be back at you again with some other webinars in the next few months. If you're not going to, if you're going to AHR, hope to see you there. There's a great event going with the HVACR school. If you're a listener of those podcasts, of Brian Orr's podcast, that would be a great place to hook up. I think you might still have a couple more tickets that are the 2 days before the AHR Expo, January 31st and February 1st. Anyway, take care everyone. Thank you for listening, and have a great evening.